Now, before we're going to delve into specific foundation models, it's important to recall the attention and transformer mechanisms. Okay, so we use this analogy of attention in the past. We have here this person in the middle who is, say, about to take a job interview, and she has her skills, presented by her CV, math skills, and so on. Now, she wants an opinion from a set of experts. Every expert is an expert in specific topics, in specific aspects. Okay, one is strong in the math and the CV. Another one is in the looks and the singing or cooking or presentation. Okay, and our candidate, our person, is interested in specific skills: CV, math, and presentation. Okay. Now, the end result is a grade that consists of three components: greatness, coolness, mastery. So she goes to these experts and asks them for their grades. Okay, greatness, coolness, the mastery. But how do we combine their inputs? Okay, because again, she's interested in specific things, and each one is an expert on different topics. Okay, so this is what attention is bringing. We are basically modeling what she's interested in, which is the query, what each expert has to offer, which is the key, and then the value, what the expert actually brings to the average. And we would like to have a weighted average that accounts for the interaction between the query and the key, how well the query matches the key. That's the idea. And basically, the attention unit um, implements this through matrix multiplication. We have our query queue, okay, of the dimension of the keys. We have the keys, okay, of the observers or the experts, or the sorry, candidates or the experts. We have the values of the experts, and now we would like to take a weighted average of the values using the keys and the queries. So we take the product of the query with the different keys. Okay, that gives us weights. There is some normalization factor here based on the dimension of the keys. Okay, we transform these numbers, this sequence of numbers, into a distribution, softmax. Okay, so we have a normalized weighted average, and then we apply it to get our weighted average. Okay. Now, usually we don't have one instance queue, one query, but rather a set of queries, one for each observer. Okay, so it looks like a matrix product instead of one small queue, one matrix queue. Okay, so this is the canonical formula of attention. Now, uh, this is also represented in the seminal attention is only need paper in this way, QKV, multiplication, scaling by this DK, then a masking, which is not here in this formula, and we ignore it basically in the course because it doesn't arise in usually in relational graph and tabular data, and it's quite a significant complexity addition to text. Okay, and then a softmax for a weighted average, and then a multiplication. Okay, now multi-head means that we apply it several times with different weights. That's how we um, allow more flexibility in putting attention in different ways. Okay, each head uses a different scheme of attentions, and we combine them. Okay, we basically, extend the receptive field of the attention. Okay, so it looks like that. Attention of different Q's, K's, V's, but they all come from the same original Q, K, and V, each multiplied by a separate weight matrix, okay, in order to reorganize the data. Okay, in the end, we again reorganize scale the data using a final matrix that will bring us also to the dimension that we want in the end. Okay, and this O plus is basically the concatenation of matrices. Put them one by one. Okay, now there is also the distinction between cross attention and the self attention. And basically, this QKV come from some representation of our uh, observers, X, and our experts, C. And the queries are obtained from X by multiplying by some matrix, the keys and values by multiplying by some corresponding weight functions, or weight matrices. Okay. Um, it is important to understand that each of these W's, well, basically, what does it do? It transforms us from the um, representation space of the semantic input, the observers, the experts, to the representation space of the queries, keys, and values. Okay. In particular, it's important to realize that these weight matrices, where every entry is a parameter, this is something that we learn. These matrices are of a size that does not depend on n, the number of instances, the number of observers, the number of experts. That's important because this means that we can train them using different sets of different sizes of experts and observers. Okay, now where do cross attention, self attention come to the picture? So there are two scenarios in cross attention. Um, uh, this is basically what we've been looking at. The observers and the experts, context item, are different creatures, and X and C are not necessarily related. Okay, so it can be the case that a textual question X is looking at components of the image, okay, at the pixels or blocks of the image. So that's an attention from the text to the picture, or from English to French. Okay, in self-attention, this is the same set. Items are attending to each other. So the observers and the context items, the experts, are the same. And so in this case, we'll have that X is the same as C. Okay, and in language modeling, for example, the different tokens of the same text are attending to each other. Okay, so this is an important distinction. And transformers build the core component of transformers are the attention, and transformers are basically just applying the attentions multiple times to the input. You have some input encoding, then n layers of multi-head attention, okay, each followed by some post-processing of the data, some feed-forward network. It includes a skip connection, okay, to allow the output of the attention to read directly the input, okay, to deal with learning training anomalies. And in the end, you have a decision layer, which is usually a simple neural network layer, nothing extremely fancy, and followed by some softmax, which means that we are basically looking at classification modules. okay, or models. Okay, so it looks like that in the original attention is all you need paper. You have a self-attention between the input items. Okay, so these are basically attentions between the prompt among the words of the prompt, and then you have a set of output tokens, and you have attention between them, and also accounting or attending also to the input elements. The positional encoding is basically used for ensuring that node or text element, a word, a token, is looking just at the previous tokens and not the future tokens. We don't have this concept in relational learning. That's why I'm not getting into that. But let's look at the use of the attention. So we have let's look at this one, which is simpler. We have the attention. Okay, we have this connection, the skip connection. So you add the input to the output and normalize. You apply a feed forward layer, again, skip connection, and that's one step. You apply it n times. Okay, each layer with its parameters. Okay, and once you're done with these layers of attention, you're going to the end. Some linear post-processing, softmax gives you output probabilities, and again, we assume that in the end we need to make a categorical decision. Okay, so next we'll talk about specific foundation models now that we understand what foundation models mean, and we got the chance to recall some important concepts on attention and transformers.